So there were a lot of questions on Piazza, and so my plan is to go quickly through the lecture and then answer as many homework questions as I can. And so it's not an accident that there are a lot of questions, because we're right now at this stage where you've learned the basics of how the language works, how variables, loops, arrays work, and now it comes to the point of putting them to use in non-trivial problems. And it's a different skill to do that. So it's one skill to be able to implement a simple class and figure out where the variables go and stuff. And it's quite a different skill to be able to put those building blocks to use to solve more complicated problems. And both skills are important. And so what typically happens at this point in the course, everyone is all happy that they've gotten past the first hump, and then they say, oh, it's getting more complicated again, how's that? And it's just the way it is. It is an entirely different thing. So I will spend as much time and as much explanation as necessary on those homework things, but I do need to advance with the lecture, so let's do that stuff real quick. And that is, oh, I didn't link to this. Okay, sorry about that. So it's lecture 22. Just click on 21 and change just click on the on Monday's date and then advance it. I'll update it. So this is actually a pretty easy and a fluffy topic here. So we're just putting algorithmics beyond us for a minute and want to put in perspective what do you do when you need to write programs that contain more than one class. And that, of course, does happen when you have larger programs. So typically, at the end of the semester, you should be able to comfortably write classes, programs that use 2 or 3 or 4 interacting classes. And by the time that you're done with 151, you will have programs that use like 10, 20, 50 interacting classes without too much problem. So that does raise the question, when you have a problem, how do you find the right classes? So far, it was easy for you to find the right classes, because I would tell you, implement a class bug that has these methods. But how do you know that you might need a class bug in a real program? But presumably you might need that if you have a game or some such thing where bugs actually occur. So in general, when you have a more complicated program, you want to have some rules of thumb on how do you find the classes that you might want to use. And so certainly if you have anything that is mathematical or geometric, then you have a whole bunch of classes, points, rectangles, ellipses, that just occur for mathematical reasons. If you deal with finance, you might have classes that have big numbers, stuff like that. And then you have concepts from real life. If you do something with a banking application, you might have bank accounts. If you're doing something that interacts with cash registers, say to control something in a supermarket, you might have a class for cash register or shopping cart or any of those things. So those tend to be fairly easy to discover. And then it goes on to more abstract classes. Oftentimes you have some kind of mechanism in your program where stuff gets transported from one place to another, stuff gets processed and so on. And so you often come up with a class whose objects do the work. Like scanner is a good example. You want to read input, and someone came up with a scanner class whose job is to grab the input and give it to you. Now, random is another good example. The name random is perhaps poorly chosen. A better name would have been random number generator, because that's what it does. It's a thing that generates random numbers. By itself, it's not random. So oftentimes these actor classes end in or, and so it's very common for designers of programs to make these kind of classes. And then finally, you have some utility classes once in a while that are often a dumping ground for methods that don't actually work on objects, but that just process numbers or arrays or some such thing. So the math class is a good example. That has these methods like sine and square root and stuff that you just need to process numbers. The character class is another good example. It holds methods such as is-space, is-letter, is-digit, and so on that you need to analyze characters. Now, the biggest rule of thumb is that you don't want to turn actions into classes. So when you have a class and one sees that all the time with beginning students, that there would be a class that's called Compute Paycheck. That's not really a class. That's more, that would be a good name for a method, but it wouldn't be a good name for a class. A class is a factory for objects. So classes, like you can have any number of bank accounts. You can have any number of scanners for that matter. One of them might read from the terminal, and some of them might read from files. And so these are objects that have their own behavior. They do stuff. Compute Paycheck is not something where you would want to have 5 objects of that class. It's not something that has some kind of autonomous behavior. So the rule of thumb is that a class should have as its name a noun, and it should be of that it should make sense to have objects of that class, with the exception of a utility class such as math. It doesn't make sense to have multiple math objects. That's just like I said, the dumping ground for these methods. Yes?
If you make like a bank class with that takes bank account classes like you're doing, would it make sense to make a teller class that would do all the...
Yeah, well, the question whether it makes sense to make a teller class or not totally depends on what it is that you're doing. So if you're doing something where you might want to pay the tellers, or where you might want to monitor the tellers to find out which cash registers are leaking money, then a teller class would make perfect sense. So it just totally depends on what the actual application is. That's actually another interesting thing. Once you get into 151, what people will often do is they're given a problem description, and then they'll make every single noun into a class. And that doesn't work either, because then you have too many classes. And so it's the job of the designer to figure out which of those classes do something useful and which of them are just fluff. So as an example, when one has an application that, say a store application, and the description says, oh, the store sells toasters and microwave ovens and vacuum cleaners, then it's not clear that those should be classes. You probably want to have a class product or some such thing, and the toasters and microwave ovens should probably be instances of that product class. Because from the point of view of the store, there's nothing, the store that sells a microwave couldn't care less that there's actually a microwave in the box. For the store, what matters is it has a price, it has a size, it has a profit margin, that kind of stuff. So it requires some amount of judgment to figure out what classes ultimately are good classes for a particular application. And so a good part of the rationale behind these sections here is to just prime your mind for that, so that when the going gets tough in 151, that you've thought about this at least at one time before that. So we're still not at the point where you're going to be having to discover a lot of classes, but there may be an assignment or so coming in 46A or 46B where you're going to be given more leeway and you have to come up with your own classes. So the other thing that when you come up with a class is you want to make each class what's called cohesive. That means it should represent a single concept. If the class can be split up in 2 separate parts, each of which represents a single concept, then you should do that splitting up. So cohesive means that all of the features of the class are related to a common purpose. So here's an example of a class that kind of doesn't do that well, and it's one that we've had in chapter 4, I believe. This is the cash register. So this cash register here has a method for entering payment, and that's fine. That's what a cash register does. It had other methods for processing sales and giving money back and stuff. And then down here, it has this other responsibility. And you can see it's a responsibility of the class because those things are public. So all the public features are class responsibilities. So somehow this class has taken it upon itself to define these constants for nickels and dimes and quarters. So it does these 2 separate things. It deals with cash register stuff, and it deals with currency stuff. And so it might be better to have this second part here in some other kind of class. One might have a class currency, or one might have a class coin, or such a thing. And in fact, that's what the book uses. They say, well, let's have a class coin. So I guess we're assuming we use dollar coins. So then we would say, well, a coin has a value and a name, so it might be, the value 25 cents, and the name would be quarter. And so the coin knows about the names of these items that we use to make payment and their values. Then the cash register, now we can change it so that the enter payment method now simply takes, one might now have to call it more than once, or you might have to give it an array of coins. Here we're just going to call it more than once for each coin type. So now we would say, okay, the customer put in 2 quarters, and that would mean 2 objects of this new type. Now at this point, note that the cash register no longer has to know anything about what coins exist in the United States. It simply takes the coin object, it calls its getValue method, and then it knows what was put in there. So this cash register would work equally well in Canada or in Mars. It would just receive different kinds of coins. So we've decoupled those 2 aspects. So now the cash register worries about what it means to process sales, and the coin class worries about what it means to represent monetary values. So that's a common thing that you do when you find that a class is not cohesive. You break it up into 2. Now, with the classes that you've seen, you've probably not seen very many of classes that are bad in that regard, classes that mix 2 different aspects, because the classes that we see in the standard library are generally pretty good, and they don't munch totally different stuff together. But when you start designing your own classes, it's just very common to see students putting too much stuff into a single class. Okay, so we want to maximize cohesion within a class. We want to have the methods be related to each other. The other concept here is called coupling. Let me first explain what it is. So another way of saying coupling is to say dependency. And so a class depends on another if it uses objects of the other class. For example, the cash register, as it was just redesigned, depends on coin. You can see it depends on coin because it has coin here as a parameter type. For all you know, the cash register might internally have an array list of coins. So anytime that one class uses another, we say it depends on that class, which makes perfect sense. Notice, however, that coin does not depend on cash register. The coin class has no conception that there are such things as cash registers. The coin class just stores names and values of coins. What happens to those coins is of no particular interest or knowledge to the coin class. So that's kind of nice that the coin class is not usable in contexts other than just cash registers, which, if you think about it, this stuff over here wasn't. Right here, if I just wanted to worry about nickels, dimes, and quarters, I'd also have to schlep a cash register with me, which is kind of weird. So now the coin class is decoupled from the cash register, and that's good. So what we generally want to do is we want to minimize the coupling between classes. And so there's a visual notation that one often uses for this. If one class depends on another, one draws this dotted arrow on it. And this is a notation that you may have seen in BlueJ. Let me pull up a couple of BlueJ projects. See over here? You see that same notation, there's the dotted arrow. Here it says that the tester class depends on the rectangle class because presumably it used it. The tester constructed rectangles, called methods on rectangles, and so on. But the converse is not true. The rectangle class doesn't depend on anything. There's no arrow from the rectangle class. So you can see it just stands on its own. So generally, you kind of like classes that stand on themselves, by themselves. You don't like to have a lot of coupling between them. So some amount of coupling is fine, too much, bad. So that's kind of an easy concept. And see, do I have? Yeah, I'll have an example for that in just a minute. So right now, when you only have 2 classes, you don't really care about that. But once you have 10 classes, you will start caring greatly. A few more concepts. You know about accessor and mutator methods already. We talked about that in chapter 3. An accessor method is a method that does not change the state of an object. A mutator method does change the state. So for example, with a bank account, getBalance is an accessor. You call getBalance and it gives you an answer. It does not change the account. And you'd be upset if it did, right? If you had a bank that charged you just for finding out how much money you have, which one wouldn't put behind past banks these days, that would not be nice. So you can call getBalance once or twice or 1,000 times, and as long as no mutator happened in between, you always get the same answer. And that's useful and comforting. Now, mutators do change the state of an object, so the deposit of a bank account changes the state of the bank account. Now, so what? That seems just what objects are all about. Objects are there to give you answers to questions, but it's pretty intrinsic in an object that once in a while their state should change. Or so people thought for a long time. So the traditional view of an object was that objects are inherently mutable, that objects live to mutate once in a while. And so the traditional thinking was that you would want to have a few mutators in your class. And that's why the first example in the book is this bank account object. So the bank account is a very characteristic object that has mutators and accessors. You can deposit and withdraw and change what's in the object. And then you can find out with getBalance what is it that you did. It's like the simplest mutable object that you can think of. But recently, in the last few years, there's been much more interest in immutable classes. Now, an immutable class is one that has no mutator methods at all, that can never be modified. And at first glance, that sounds weird. If you can't ever make any changes to something, what's so great about that? Right? I mean, it's the Republican mind or something. So the way that nowadays, though, we think about it is that there's one great advantage of never being able to change something, and that is that you can give out multiple references to different processors. And those different processors can all look at your object in parallel, and there'll never be a situation where what they see depends on at what time they made that query. And why do we care about that? Because computers nowadays are no longer getting faster. We're just getting more processors. And so we're now caring about an architecture of the software where you can have your data structures inspected by multiple processors at the same time without having any timing issues. So you're going to be seeing more about immutable classes. And you've seen one, namely the string class. And has it actually ever bothered you that you could not mutate a string? I mean, have you woken up at night and say, gosh, I wish I could mutate that string and make it into a different string? Because after all, if you did need a different string, what you did is you took a substring from before where you wanted to make the change, a substring from after where you wanted to make the change, and you glued that stuff together. Now you got a new string, also immutable, that had to change. So, not having mutability is not deadly. And so I'm not advocating that every class should be immutable, but it does make some amount of sense for some classes to be immutable. And when you design a class, you should ask yourself, should this be one of them? As an example, the location class that I talked about last time for a location in a grid has a row and a column. You could design that location class so that it has a move method. So you could move a location across on the grid. That would be a mutable location. Or you could make it so that it doesn't have such a thing, and that would be immutable. Another example would be the rectangle class. Let me just show that. So remember the rectangle class that we've been looking at since chapter 2. Is it mutable or is it immutable? So once I constructed a rectangle, I say Fred is new rectangle 5, 10, 20, 30. Can it ever change? Or is it like a string? When I make the string hello world, it never changes. Is there any method on rectangles? What methods do you remember on rectangles?
Get
Get
width,
width and get height. They won't change it.
translate,
Translate, yes. Translate mutates it, right? Translate takes it from here to here. Now, was that necessary? Maybe not. What they could have done is they could have made translate so that it returns the translated rectangle without changing the original. Just like to uppercase returns the uppercase version without changing the original. And so the more modern thinking is that probably would have been the better way to do it. With simple objects like that, where there's no particular need to have mutability, it would probably be better to have a method that just returns the answer, leaving the original unchanged. If someone wanted to change a rectangle, they could just capture the new one and remember that. All right. So let's have a quick self-check here. Not a self-check, what do you call it? A clicker question, I don't know. Oh, I copied and pasted it wrong. All right, so let's go to Piazza. Clicker question one. All right, so let's see. So get balance, now it's implemented to say public void get balance system out print on balance. So now if you want to know what's the balance, you call get balance and you look up what happens. Okay, is it a mutator method? It's not, right? It doesn't change the bank account, so that can't be right. Is the bank account class now immutable? No, right, because it still has deposit and withdraw, and those are mutator methods. Does it increase the cohesion of the bank account? I don't even know how to begin to make sense out of that statement, so I hope not too many people chose it. Does it increase the coupling of the bank account? With what class is a bank account now coupled? System and print stream, right? So now it's coupled with two more classes, and we say extra coupling is bad. And so in abstraction, of course, it's bad, but let me also explain why it's bad in concrete terms. Okay. So So let's say we print it. Come on. And that's true in any method that prints. First of all, it means that now your class is only useful in an environment where you can print. Is there any environment where you can't print? Have you ever seen a computer where you could not print to the terminal?
Original Mac OS.
How do you print on your iPhone or on the Android or on a tablet, right? So we're now at this point where the majority of computers are no longer our desktops. You know, that was your dad's generation. That was my generation, right? So nowadays, most computing devices have no particularly natural idea of what system out println might mean. You know, with the Android, I can actually look at the system log, but with an iPhone, I don't really know. So you have a lot of systems nowadays. Any kind of embedded system, the computer that drives your car, does not have system out println, right? Where would it appear? You know, in some paper tape in the oil pan. I mean, it means that you're now designing something that has this really unnatural dependency. Now, every once in a while, I do give a homework assignment where I have to print something inside a class, but every time when I do that, I say I shouldn't be doing that next time. I should really always make you return a string. So, I don't know, do we have one in homework? This is actually a great segue. No. So in this homework, we're doing good. For example, here with the men's room, instead of having you print out what is the state of the men's room, I'm making you return a string that describes it. And then it's up to my program what I want to do with that string. Do I want to compare it with another string? Do I want to print it out? I still have that option, of course, but it's no longer coupled to that. I believe in the previous homework that was not the case. No, this one was good, right? The pretty toString returned a string. Where was it? Maybe it's the next one. So every once in a while, I didn't want you to do it because somehow I was afraid that stringing together a long string with multiple new lines was confusing, and so I didn't do it. But I should really rethink them all. All right, that's kind of all that I wanted to talk about the lecture. I put in some other stuff here in the slides in case I need some extra time. So if we run out of questions, I'll go back to it. But I did want to spend some amount of time on good old homework 11. So, is up then down. So what was the idea? So we have some sequence here, and we want to know, does it look like this? So let's look one that does look like this, and how could we verify that? So it seems that a key idea here is to look at the difference between successive numbers. And when we look at the difference, we probably only care whether the difference is positive, negative, or zero, right? We don't care how much the difference is. So let me just write that here and say here the difference was 1, here the difference is 1, here the difference, oops, it's minus 1. So it seems fair to say that if I see a pattern of these differences, where I only look at their sign, where the pattern of difference is plus 1, plus 1, plus 1, followed by minus 1, minus 1, minus 1, then it first goes up, then down. Is that right? Would that be universally true? And it would have to be, right? Because if you, plus 1 means you go up. So you go up, you go up, you go up, and then you go down, down, down. That means you go up, and then you go down at the end of it. If, on the other hand, you see +1, +1, -1, and then another +1, that means you went up, up, down, and then up again, and then it's false. So with this insight, this is now a pretty trivial problem. Now let's go to implement that. One way to implement it would be, I have an array. I could build an array of these differences. And then once I have that array, I could check, does it have a bunch of +1s and then a bunch of -1s? And that would work. Do we need the array? Well, probably doesn't really need the array in this case. You just need to have some memory built up. And that's now a little bit trickier to build up, right? So what I need to have remembered is the previous difference. So I need to remember the previous difference, and then I now get the new difference, which is the sign of I plus 1 minus AI. And now I want to compare them. Oh, this is still too complicated for me. So let's say the previous difference was +1. It seems to me that the other thing that I need some kind of indication on which of these two areas I'm in. And one way I could do that is I could just keep a counter, and I would say the counter value is 1 when I get started, and then it is 2 when I'm in this area. So a Boolean might also work. The reason I'm slightly worried about the Boolean is I'm kind of worried what happens if I have another +1 here, but maybe I could bail out then. I think I could make a Boolean to work. My instinct is just that a counter gives me a little bit more flexibility. What I sometimes do is I first do the counter because I have then the choice of having more than 2 states. And if later I realize that I don't actually need the extra ones, then I rewrite it as a Boolean. So we might want to give that a try. So right now I would say the counter is incremented. So I should say if difference is not the same as previous, then I increment the counter. So that way the counter counts how many times I flip between ups and downs. And how do I know whether it's up and down? When the counter is 2, right? So let's try to do that. What was this thing called? Oh, that was really helpful. No, I have to write it from scratch. Okay. Do I actually need I?
Since you're going to be testing the next element
Oh, yes. Okay, good point. So I compute what? AI plus 1, no values. Minus values I. So here's the, no, I don't return the counter, I return whether the counter is 2. If the counter is 2, I return 2. Okay, I need to initialize the counter with 0. Oh, and this is not actually what the difference is. I want the difference to be the sign of this. So I want it to be plus 1, 0, or minus 1. Unfortunately, there is no predefined function for that, but that shouldn't stop me. Oh, yeah. Are they actually? I guess I copied and pasted it. There must be, yeah. Okay. So, if x is 0, return 0, else if x is greater than 0, return 1, else return minus 1. Okay, that's useful. Now, then there's this thing with the difference and the previous difference. And this is a general pattern that's often useful, that oftentimes when you step through an array, you're computing a new value, and you also want to look at what happened the last time around. And the pattern is always the same way. You compute the new value, and at the end of the loop, you say the previous one is the new one. Anytime that you need to step through an array and keep one level of computation, if you have to keep memory one step like that, that's the pattern that you use. So the only issue here is whenever you do that, you have to worry about the first time. The first time is always special here. And so what do we want to achieve the very first time? We want to make sure that whatever the difference was, that it's not the same thing as the previous one, because the first time we want to increment the counter from 0 to 1. So it seems like I could have the previous difference to be 99. That way it'll always increment that counter. Oh, 99 sounds pretty arbitrary. So I'll put a comment here to explain this strange choice here. And now the only other improvement that I could make is I can make this one a local variable, because diff is not needed outside the loop, and it's always good habit to make things as local as possible. Previous diff is needed outside the loop because it needs to persist over more than one iteration. Okay, let's see if it compiles. Yeah, do we have a tester? Yes, we have a tester. Huh? Oh, because I didn't call it arrays 1. Oh, that's annoying. This is one thing that I dislike about BlueJ. When you accidentally misnamed the class, you have no choice. You have to make a new one. There's no rename. Let's get rid of this.
Actually, if you open the editor and change the name in there and compile.
Oh, it'll change it?
Yeah, it will. Like, if you go to
Huh?
tester and rename that tester two,
All right.
at the top and hit compile, it'll rename it.
Thank you.
You can go back to your DJ.
You are right. Oh, great. Well, I learned something. That is totally good. Okay. Okay, should have done that. All right, let's run the tester. Ay, ay, ay. And I'm get. Yeah, so here I'm getting an array index out of bounds exception. And so what happened here is I had the very standard loop here from 0 to values dot length. And I did have a less than here, because of course I don't want to go up to values dot length. But when you look at I and I plus 1, then you have to subtract 1 here, because otherwise it'll blow up at the very last position. And actually, that makes some amount of sense, because when you look at the picture, no, if you look at the previous picture, let's see if I can get it back. No, I can't. Let me draw it again. Notice that you have one less set of differences than you have the original values. So that accounts for this -1 here. Okay. Let's try it again. True, true, false, 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 false. So that looks good. The one thing that I would be a little nervous right now is, what if it started with a 0? But I think I'd still be okay. Okay, I'm going to leave it at that. In the interest of time. And when you think about it, this is actually a useful way of doing the next part, right? I think I've given away a good part of that, because when you want to count the ups and downs, oh, actually, there's a bigger mistake in here. What's the big mistake? No, no, I fixed that. And it's interesting that none of the test cases caught that. Right. So what am I doing? I'm checking whether the number of transitions is 2. So if I had a path like that, then it passed. If it was like this, up, down, up, it failed. If it was like this, there would be just 1, and it would fail, and it should fail. What about this situation? It'll pass, right? Because it'll first count the negatives and then the positives, and it shouldn't pass. Let's first of all verify that it does break in this case. So we'll make a new test case where we expect failure, namely if it is 3, 2, 1, 2, 3. Right now we expect failure, because that's down then up. It's not up then down. So true, true. Oh, I meant false. Okay, let's just pretend I said false. But you'll see, I expected false and it was true, and that is exactly because my logic was wrong. How do I fix it? So I need to rule out
You put initialize counter 1
Oh, that's very clever. I could make previous diff to be 1.
You've added an extra one value.
Yes. And I would have the counter to be equal to 1.
Well, actually, assuming the value is,
This would work because then it would say, it would basically say if it continues its upward climb, then you don't count that. And so,
still got an 11 on the value spot line.
oh yeah. Thanks. Oh, and let me change that fail to false, because I meant it to say false. True, true, false, false. Okay, now they're all good. So I'm still not totally convinced that everything is right. Now I'm going to start worrying about sequences that are flat somewhere in the middle. So if you have something that is constant for a while and then goes up.
But for 0, doesn't it increment the counter?
Then you say it increments the counter. Yes, you're right. All right. So that's a good observation. So he says that if that really what we're getting is we're getting there's 3 types of segments. There's flat, up, and down. And right now, if you had a situation like this, that would say there are 3 segments, would count them as 3. Yes, excellent. All right. So what I wanted to point out is this is now a good framework for for the second method in here. Where do I have it? For the ups and downs. So that's we already now counting how many ups and downs there are, and at the end we say if there are 2, then we're happy. And so the idea of the counting is already there. There is a little bit of a twist now, though, with the flat segments that should not be included in this count. So you need to figure out how to get rid of the flat segments. But you now have a pretty good idea on how to get going with that. So if one reflects on, people always ask, how do I get started? How do I get an idea? And so the way I always get an idea is to get out a sheet of paper and to look at some sample numbers and see how could I do it by hand, restricting my mental abilities to those of a computer with this particular sample. And then I would look at a few more samples to see what other behavior there can be. And once I have that basic idea, then I can start looking into my toolbox and say, what do I need to do? Oh, I need to make 1 pass through this array. I know how to do that with a loop. I need to remember something and the thing before that. Oh, that's the trick with the previous thing that gets updated at the end of the loop. I only care about the fact whether it's positive, 0, or negative. That often happens, actually, that you only care about that and you don't care about the actual value. And then it really is useful to reduce the number to its sign. And, of course, a lot of these things are from experience that I've done it a few times. But I can't overestimate what really is important is that you first have an approximate idea on how to do it by hand before you start opening the IDE. I often get students who start opening the IDE and then they say, what letter should I type next? I have an answer to that, and that's P, because after all the method starts with public, but it doesn't go much beyond that. So you really want to first doodle on paper and come up with a design. So let's try that with the next one here. Copy with negatives first. Return a new array with the same values in which the negative numbers come first. All right. Yeah?
For the array lists, if you add something at an index, does it just move everything else up, or does it replace that index?
It moves.
It moves everything?
Oh, yes. Oh, yes. It's in the book. There's a picture that shows how the movement works. So let's take one that has some positive numbers and some negative numbers. Which ones should go first? Negatives first. So now what I'm supposed to do is come up with a new array. And let's see, so I'm not moving this one, I'm not moving this one, I am moving this one here. Not moving this one, I am moving this one here. So now I've gotten the negatives in the front. What about the positives? Well, I can do it again, right? There's no law that says I can't do it twice, so now I'm making another pass through the array. And I say, fine, now this one goes here. And now I know a lot of stuff about this problem. I know that I need to make 2 passes. Did you know that before, when you first looked at it? So I knew this without writing a line of code. I also know something else. I know I need to have an index variable here. Why? Yeah? Yeah, I need to know where to put the new thing, right? Because in an array, there's no way of putting something at the end like there is in an array list. In an array list, I can just say add, but in an array, I have to remember where to put stuff. And so I need to have an index into which I put something, and then I increment it. Put something, increment it. Put something, increment it. So that pattern is going to have to be there. I also know something that's probably pretty obvious, but it wasn't totally obvious to me 2 minutes ago. I know the size of the array that I need to create. It has to be the same size as the original, right? Which, from the picture is blatantly obvious. So I'm now in pretty good shape to probably code up the entire thing. And I won't do everything, but I'll do enough that you'll see the structure, and you see that the structure is totally related to the drawing. So this is arrays 2. So I know this much code already because I need to return an array. It says so, right? So I need to create the array somewhere. Might as well do it on the top. And then I need to return the array. Now, I'm in the fortunate position that I know how big it is. That's half the battle with these things. I also know I need to have an index into that array. And I'll call it last filled. It's the last one into which I already put something. I know I have some loop. And I'm assuming for right now there are 4 loops because I traversed the entire array. And in here, I'm going to sometimes, if some condition is fulfilled, I'm not always moving stuff, only sometimes, I'm going to say last filled plus plus, and what is the result? Last filled equals something. And I know that that loop occurs twice because when I was playing through this thing, sometimes I saw myself moving it in the first pass, and sometimes I saw myself moving it in the second pass. So you can see from just playing it out on a sheet of paper, you can see the basic structure of the code. And that's a really useful observation that, and it's no longer such a trivial structure that you could just do it by random trying stuff out, right? It's not just a single loop. But you can see how by just looking at what you do by hand, if you translate that into the programming language, you get ahead. It does mean that you know how to do some tricks. So here, where I said, this kind of basic thing that says, increment an index to the next one, and then put something there. That way you can fill up an array one slot at a time. By the way, you don't have to do it this way. You could reverse that. You could say, if you don't like the -1 here, and many people don't, you could call it next to fill, start with 0, and then you could do it like this. So it's the same idea. Now I have a variable that points to the next location that should be filled. I'm starting at 0, and then that's where I'm putting my stuff, and then I'm incrementing it. Maybe this is more natural, I don't know. Either way is fine. All right, so now I was asking, do I need, in this for loop here, do I need index values? Whenever you write a for loop, you have two choices. You can say I goes from 0 to values.length, or you can say just value colon values. So do I need to know the positions of the elements that I'm looking at? So let's look at the algorithm here. I looked at the 10, I looked at the 10 in the first pass. I didn't want it. I looked at the 12, I didn't want it. I looked at the -13, I did want it. Did I need to know where they are? No, I just needed to know what they are. So over here I can say I can just do it like that. Same thing here. The second one is exactly the same loop as the first one. Right? There's no structural difference. So, but I needed to know something about the value. I needed to know, was it negative? All right, now that we have this basic code here, we could ask ourselves some question. Did I really need to make 2 passes? Could I have done this in a single pass? No, because when you saw this 10 here, how would you know where to put it? You wouldn't have known where to put it, right? But now suppose that what you had was not an array, but an array list. Watch me now. I'm looking at the 10, and I'm just going to put it in the result. It's an array list. I take the 12, and I just put it in there. I see the -13. It's negative. And I'll insert it in here, in the front, which now flattens the whole thing out to -13. 10, 12. I see the 14, and I put it here. And I see the -15, and I put it here. Only one pass. Provided that somehow I know where to put them. So what's the rule? Where do you put the positives? So like, where did I put this 14 when it came? At the end, right? That's actually very easy for an array list. There's a method for that called app. So the positives seem to go to the end. Where do the negatives go? Well, that seems to kind of depend. The first negative went into offset 0. The second negative I had to insert before offset 1. What if there's a third negative? Where do I put it? After offset 2, right? It goes, now the 15 is in here at position 1, and then the third negative goes in here. So it looks like every time I see a negative 1, I need to increment some counter, and that tells me where to put the next negative. So I'm counting the negatives. Do I need to count the positives? No, because they always come at the end, and so the array list knows how to deal with that. So if I wanted to return an array list, which was not one of the choices that I had, that would be the algorithm. Okay, that would be easier. So array lists are nicer. All right, but that was unfortunately not what the homework asked about, cruelly enough. It asked and said something entirely different. It said, what if I'm not allowed to allocate another array? See, all of these things are easy if you're allowed to allocate another array. But now I'm not allowed to allocate another array. So cruelly enough, I now have to do the same reordering, but I have to do it in place. Now we have to do this with an array, and we have to do it with an array list. The second one is with an array, and the third part is with an array. Which one do we want to figure out first? Yeah, you always want to figure out the array list first because that gives you more tools. And if you can do it with an array list, you can surely do it with an array. So let's figure out how we would do this with an array list. So I'm looking at the 10, I say, no problem. Stay where you are. I'm looking at the 12, no problem. I'm looking at the minus 13, and I say, oops, that should be somewhere else. What do I do? I can remove it from here, and I can insert it in here, because in an array list I can do such a thing. Now with the 14, I don't do anything. And I'm now looking at the minus 15. And what do I do with it? Well, I'll certainly remove it from here, and then I want to insert it here, right? So it's kind of similar to what we just talked about. You need to keep track of how many negatives you've already moved forward so that the next one goes there. So if you now look at the ingredients of this process, so it looks like you need a loop. How many loops do you need? Well, just watch what I did. I looked at the 10, I looked at the 12, I looked at the minus 13 and I moved it. I looked at the 14, I didn't do anything. I looked at the minus 15 and I moved it. How many times did I loop over them? Once, right? So we need one loop. Inside the loop, we'll make a decision on whether the current element is negative or not. And then if it was negative, we move it to some as yet undisclosed location. And if it wasn't, then we do not. So we already know the basic structure of this program without ever having written it. We have a loop. If something is negative less than 0, we remove it. Is it insert or add? I can never remember. Add, right? And we add it somewhere. And we have to increment some kind of counter. And so I guess the position is somewhat related to the counter. You know, maybe +1. Might be some kind of an offset there. And so that's the basic structure of the program. We didn't have to create any new data structures. We just shuffled around in this existing data structure. And we knew all of this by taking the algorithm that we've developed on a sheet of paper and then translating the bits and pieces into Java. So people always say, how do I get started? And that's how you get started. Sometimes I see people when they program, they do something very odd. They type the first line, and then they start worrying what goes in the second line. And then they worry what goes into the third line. Notice I didn't do that at all. Right? I just said there is a for loop. And the for loop has a bit of stuff in here, and it has a bit of stuff in here. And then I said there is an if statement, and I know it has to go inside here, and then I put it in. I didn't develop it from top down. It's not like an English novel. And I'm sure that people who write novels don't write them from the top down either. They probably write bits and pieces in the order that makes sense to them. And it's the same thing with code like that. So I'm not at all bothered right now that I don't yet have all of the answers. Those dots, I'll fill them in later. I've filled in a million dots in my life, and I know that eventually I'll be able to figure out what kind of loop that is. Over here, I put in the dots because I didn't even want to worry about yet, how do I get this value? Is it values.get of I? Is it values bracket I? Is it something that I had previously gotten already? I'll just say there's something that I need to check for less than 0, and I put that in. And that way I can develop these algorithms outside in. I know how to do it by hand, and now step by step I can translate that. So now at this point, now I'll have to start worrying, oh, I need to remove something from a particular position. Remove wants to know the position. And so that means I know I need an integer index, so now I can say, oh, so, and the one that I need to remove, well, that's going to be the one at the current position. So the one that I want to look at, that's going to be values.get. Now, where do I want to add it? So the one that I do want to add is, oh, phooey, I just removed it. So I should have stored it somewhere. I see, and now I'm falling into the no more than 3 variables.
You don't need the current value.get I.
I'm going to show you how to get rid of it. So over here, so that's kind of an artificial restriction. I don't know why I put that in there except to be a pain. But here's how you can deal with that. So I would put the values.get back here. Now it is true that when you remove it, now you no longer have it, so how are you going to put it back? But as it happens, and you've heard it here first, values.remove is nice enough to return you the value that it has removed. And therefore, you can put it in here. Now isn't that nice? That should have been worth the price of admission alone. Right, so that way you now have 2 variables. Oh, the question, because I wasn't sure when I wrote it whether it's exactly counter or counter plus 1 or counter minus 1. And so what I often do at that point is I just put in the plus question mark. That way it will not compile. And if later on I forgot that I hadn't made that decision, then I remember. Because, again, what's important when you develop these things is you don't want to get bogged down into all of the details right from the beginning. You want to say, okay, I know how to do it by hand, and that's valuable knowledge, so let me put that knowledge into the code. And once you have captured that in the code, then you can start systematically settling all of the various minor questions that you have, like, is it off by 1 here or some such thing. Yeah, same thing with initializing variables. That's something you don't have to worry about it right the first minute that you have the good idea. The important thing is the good idea, and that's a hard thing to have, right? You have to develop a good idea, and so you don't want to lose that. You don't want to get bogged down into details. There are a million details with these things, and that's what everyone, I'm sure, experiences right at this point, that it is a lot of details, and there's a lot of room for error. And so what I've been trying to show you is a way to get from here to there. And so that way is to first get the idea on a sheet of paper, just doodling around, figuring out how can you do it by hand, or using coins that you move around like we did in one of the labs. There's something that gets you the idea on how could you tell your younger brother how to do this. And after you have that, then you have the secondary task of translating that idea into code, and then the final task of making that code work with all of the fiddly details. And so I wanted to focus on the first and the second part, not so much on getting the code and all the fiddly details right, because that's something that you already know how to do. All right, so